introducing myself, I was doing my PhD in Leeds before joining ECMWF, and that's when they had a lot of position for AI. And my PhD was using deep learning for groundwater modeling. So it kind of fit well within the position there was AI for hydrology. So yeah, it has been now 1.5 years since I've been working there. And my task was to try to develop a deep learning model for hydrology. And then as time grew, then kind of the team grew up a bit. And so it's a joint work. But yeah, you should see the slides moving. Let me know if they're not. But yeah, I will start by introducing why floods. Or maybe just to add, just feel free to interrupt me anytime, just to keep it quite casual. Yeah, and I'm also very happy to, whenever I'm in Leeds, to have a coffee and discuss more, like in person. I also didn't really introduce ECMWF, so if there are questions about that, I'm happy to, or whatever is happening in the AI space at ECMWF, I'm happy to respond. But yeah, let's dig into the problem. So I will introduce why floods are important and why we're doing that, and then why deep learning for floods. So what we developed and kind of how the model is performing, and then a bit about the operational pipeline, as we are on both a research but especially an operational center. So that part is also quite important. And then what's the future work. Why are floods important? Because are the deadliest and most expensive natural disaster. Lot of people are affected, and of course floods are now becoming even more frequent with climate change. And the economic losses, especially in Europe, it's now more about rather than casualties, it's more about economic losses. That are really increasing. So having a prediction and forecast is important to lower mortality, to lower the economic damages, and it's most needed in low-income countries where the flood risk and the impact of climate change is greater. However, the data can be a bit challenging. So that's a bit the difference, or actually the main difference between this type of work and the AIFS type of work. So I'm not sure if I follow that space of the AI for weather forecasting. I think that my main takeaway is the difference is that in that space we have ERA 5. And now there will be ERA 6, which is a beautiful data set, or I mean, not beautiful, but it's like continuous in space and time. Whereas we actually don't really have something like that in hydrology, which is a bit of a challenge. So some of the challenges that is that the phenomena are complex. So whatever is happening upstream is causing what's then happening downstream. So if there is, say, a release of a dam upstream, then it's gonna affect the whole path downstream. And between two points in the river, you cannot simply interpolate because you might have an affluent in between. You might have something in between that actually doesn't really allow you to easily interpolate between 2 points. Yeah, so and river networks are not comparable. So a river in Africa is completely different than one in the Amazon. So just to give a bit an idea of how we represent a river, is actually you can think about it as graphs, or at least that's the way we represent it in GloFAS, which is our physical model. So yeah, I think in a way to very much represent the river in a deep learning way is a graph neural network. However, that's not the approach we have used up to now because that's not yet really developed. Like literature has not really shown that method is the graph neural network superior. But this is just to give an idea of how the river network can be represented and how two different, so the grids and GloFAS represent the same river, but actually are quite different as well. Another challenge is that, as I said, the data are not continuous in space, and they're also quite, so they're very sparse. You have areas that are very highly observed, where, for example, Europe is highly observed, but you have areas in the world that have very sparse observation. And the observation are also heterogeneous, so you can have the handwritten ones, so they are very high level, so they are kind of not comparable. And then what you also have is that all the kind of hydrological service, they apply their quality control, but their quality control is always different from each other. So you kind of have all kind of quality checked and quality controlled and filtered data, but they're kind of different. So the observation, the data that we have are very heterogeneous. And the quality as well. So we're very uncertain about the quality. Sometimes you have just peaks because there is actually a flood event, but some other times it's just the sensor that is it's an outlier of the sensor, and a lot of missing data. So this is the data set we have been using, and this is the Caravan data set, which is actually a very nice kind of open source initiative by Google. What they did is that they provided a set of tools, a script, and people or authorities could just upload their own data and kind of standardize them using those scripts. What you see here in this plot is. On the left one is the availability of the data through the years. So you could see that that in the last few years, this data set has very few data, which is of course a problem because in principle we want our model to really be the most modern, using the newest data as possible. And then as you can also see, it's you have some areas that are very highly measured, especially in North America. We have a lot of data, whereas other areas that are completely empty. So yeah, and I think also a problem with this data is that they are highly sensitive. So if you have a flood and you might not really want to share, so the authority might not really want to share their data. So it's really difficult, and a lot of these data actually have licenses and are like their usage is restricted. So we also have some data in ECMWF that we cannot even use ourselves because they are restricted and are only they can only use for certain purposes. So that's also a bit tricky. And then another challenge is that the non-stationarity. So things happens, the sensor get moved, and of course you have a lot of human influence. So if you decide to build a structure in the river, they are completely going to change the how the river is functioning. So if I train a model based on the past data, I might completely miss how it's actually going to behave in the future because you have this new structure. And of course, climate change is also a problem. So if you have a river that always used to be, I don't know, that in if it's really driven by snow melt, say, but now the melting of snow as the patterns has changed, and the water in the river is going to be of different magnitude. So what you see in this example, let me see. Yeah, there we go. What you see in this example, which I quite like, is that when we were looking into this data set, the Caravan data set, we could find some points where, so in this case, you can see in the top left, you have two overlapping. So there is a darker blue, which is on the top left, and then you actually these two stations are the contributing area is pretty much the same. There are 99% of the contributing area is the same. But one of the 2 points is after this structure, which you can see in the, so you see, let me see if I have a laser. So here you see that this is the contributing area, and then you see that this is the additional contributing area of one of the point, and that's this point, which is after this structure. So the other sensor is kind of just in between, just before. And what you see in this time series is that one, which is the one after the structure, is completely flat, whereas the one before has peaks. So you can see how two sensors that are very close to each other can have a completely different response. And that's, of course, a problem, because when you train a model, then the model is trying to do something that is in between. And so it's probably going to learn something that is really in between. So that's kind of to stress the fact that I think one of the main challenge in this work is really to check the data quality, then to create a data set that is that we can use. And that's a bit, so when they hired me at ECMWF, they were also trying, and still now, so there is the main AIFS development, but then there are these, what they call health system components. So there is pretty much 1 or 2 people per topic. We're trying to develop AI model for each of these. So for example, for waves or for the land component, and me and then recently another person, Kenza, joined. We're working on the hydrology one. And what we all saw is that actually these challenges are a bit shared between all these components. So the quality of data, the limited availability of data, and so on. And you can also see that the scale of the data that we have is quite small. And that's actually because of a lot of pre-processing we do on the data. But I'm gonna come on that soon. So despite all the challenges, we do have some global operational models. And especially there is the GloFAS model, which is developed by the European Commission, the Joint Research Center. And it's so we operate it. So we are the computational center at ECMWF. And then it's also run with our forcing. And then the other kind of very interesting model is the Google model. So they, a few years ago, they showed, actually it was in 2024, they showed how their model, which is now open, you can go in Google Flood Hub and look at the real-time operational model. And they showed how their model outperformed GloFAS. It's kind of a bit, I mean, yeah, of course, Google has a very big public department as well. So of course, you have to really be careful of the statements. But it's definitely true that the Google model is definitely strong, and in some cases outperform the physical model. Anyway, what we wanted to do is to kind of try to learn from that approach. So starting from their approach and try to see if we could kind of reproduce, but in a way also adapt their model to what we wanted and what we thought was maybe beneficial for us. So for example, what they do is that they force their model with other. So iMerge is from NASA, and it's come from a satellite product. CPC is also for precipitation, and it's It comes from some sensor data. Anyway, we are not retrieving this data, so we actually only wanted to use IFS data. And then we also did some, so we use a different loss function. We use a slightly different, or actually a different architectures. They use a tool, LSTM, and so we differentiate our methodology in the architecture, in the loss function, and the forcing. But we still kind of try to understand their methods, their method better. And also by having also talking to them. So that's why we wanted to create our own machine learning model to try to really also check how it does in operation. So let's go a bit on how this model, the state of the art, so both the Google model, but a lot of literature, how they go on developing deep learning model for flood forecasting. So what you usually have a gauge station, so this sensor in a point, and then you have and it measures discharge. Which is the volume that is in time, and it's actually used because it's traditionally used in hydrology because of water balance equation. Anyway, that's usually what hydrologists look at, is this discharge, but you can think about it as time series. So you have it in a point, but then you have a contributing area to that point. So eventually, whatever falls outside that area, so if there is a rainfall, for example, that falls outside that area, that rainfall will not contribute. So only this area contributes to that point. That's kind of pretty much the idea of the lumped, it's called the lumped model. So what we do is that we gather forcings. So you can think about precipitation, wind, temperature for all that area. Because of course precipitation is the main driver, but then temperature is also very important, because then you can think about evaporation, or say the melting of snow, and hence all the snow that comes and fills the river. But then you also want to have some attributes. So, for example, we want to know what the vegetation is, what the topography of the land is, and so on. So you gather all these inputs, and then what you do is that so say this is for example a map of precipitation, and then you only focus on that area that is contributing to that point. And then what we do is you actually really simplify simplify those data. So instead of having an input that is an image, you just calculate simple statistics. So for example, you calculate what is the daily sum of all the precipitation in the area, the maximum and the minimum, say things like that, or like distance weighted. So we are not really using, and of course something we could do and we should do in the future is to use some CNN or some as a vision technique. But what we're doing now is to simply take these averages, because they actually work quite well. So there is no need for now to look at more complex way. So what we do is so for each time step, we take those aggregations. So as I said, we do a lot of pre-processing of the data. And then we just feed it to the model, and then we get the time series out. And of course, as I talk about time series, we are actually using an LSTM. So again, there is a lot of research that is now trying to use other models like transformers or state space model. But as it is now, LSTM, despite being an old, pretty old, 20 years old model, it still seems to outperform all the other ones. And the reason for that is that it's really on the states, on how the LSTM has the state and how it propagates the state, which kind of nicely represent how also the state of the hydrological state is. Anyway, so the way it works is that you have the main core is an LSTM, and then you give this actually, as I said, they're actually time series. So these time series go through embeddings, And same with all the attributes. So you have things like, as I said, elevation and the human influence or vegetation and so on. And so it all goes through embeddings, and then it all feeds into an LSTM. So what we do have is that you have an LSTM that receives many time steps, and then it outputs what we want. So, so for example, it outputs 10 days. Up to now, it's only 10 days of the forecast of river discharge. So, of course, it also takes the, maybe I have it in the second slide. So what you see here, I'm sorry that it's quite blurred, is that you have past. So this is the initialization period. And the reason for that is that you kind of want to see the whole kind of seasonal cycle. So you want to know at which state really you are today. So you initialize your model for, we do it for half a year. And then from this point on, and so all the information we have here is the past. And from here on, we are forcing with operational, with forecast data. So we use, for example, the forecast of all the forcing of precipitation and so on. And then what we actually do is that we have a deterministic model. So we train, so that's different from Google, that they use a probabilistic loss. We just run, so we have the 50 members, so we have the 50 ensemble members of our is IFS, is the weather forecasting system, and we just feed it 50 times. So we run the LSTM 50 times, and then we get the distribution of discharge. So what we also needed to do was to have actually, so we wanted to fine tune the model. The reason for that, so we pre-trained the model on ERA 5 or ERA 5 land, which is slightly different for for the temperature, for example. But anyway, you can just think about ERA 5. But then in real time, we're actually using IFS, which is the weather model, and their distribution is a bit different than the reanalysis product. So, for example, IFS might be wetter than or is wetter than ERA 5. So you actually want to account that, you want the model to account for that wetness. So that's what you see in this top figure. You see the precipitation and the difference between the reanalysis product and the forecast at that time for lead time 1, which is just the initial step 0. And what you see here is that just the kind of how the model between being pre-trained and fine-tuned, how it kind of learns that's the fact that IFS is wetter, and it kind of tries to compensate for that. So when we look at the performance, of course, here I call it global, but as you see, it's very not global. And the reason for that is that, as you might remember from one of the initial slides, in the last few years, we had very few available data. So those are the years we keep for testing. Hence, we only have around 3,000 stations around the world. But what's interesting to see is that actually the model, I forgot to put it here, but the distribution of the error is very similar to the physical model. So you have some areas that are like in center Midwest US that are very arid, and it's kind of difficult. It's been always difficult for the physical model to learn. So kind of the parts, the areas where the LSTM struggle pretty much are the same where the physical model also struggle. And then when we compare to the Google model, we see that we have very similar performance. In particular, when we look at the station where we do bad, they are pretty much the same station where they do bad. but they have some stations in which we are performing purely where they actually are performing okay. And the reason for that is that in the Google model, they use, I think, five forcing product. So I previously mentioned iMerge and CPC, but they use, I think, something else as well besides ECMWF products. So what they actually are able to do is to learn. So say IFS is and our ECMWF products are quite bad in a region of the world. That might be compensated by other products that might be better. So that the fact that they use multiple forcing products it really helps improving the performance. So that's something that's I think we should also internally consider to just retrieve more of these external products. And then another main reason of the difference is that they use asymmetric Laplacian. So the loss function is a probabilistic loss. So they might be able to really learn more the distribution and more the outliers, whereas what we actually use is a normalized MSE, where the MSE is normalized by the magnitude of the pretty much the magnitude of the river, so as to have smaller rivers which have a lower, smaller discharge, kind of to account for the saying of larger rivers. So that's kind of the loss function that we a normalized MSE. That's how you can think about it. Anyway, we also looked at a couple of case studies. So we have just started to look at the performance, and this is one of the case study we looked at. Actually, my colleague Kenzo looked at it, and now what you can see is that, well, this is just the forcing, so the precipitation, and this is just the control, so one member. And what you see is that in this case, the model is, so this is with a different forecast. So with the, so the model could already, like a few days in advance, predict that there will be a flood. But then the flood is overestimated. And the reason for that is really the precipitation. So I haven't had here an observed the observed point, but the precipitation was overestimated by the model. So I think that's something that we could still work on really trying to maybe bias correct the precipitation, or learn if there is something that could be corrected before feeding it to the model. As it seems kind of a recurrent pattern that if the precipitation is, so even though if we fine tune the model, it still seems to really be driven by a wrong precipitation input. But yeah, so there is a part which is the research part, but then there is an all other part that is in a web, which is the operational part. And that's where really I had to kind of hand over the model to another team, kind of work together with them, but try to leverage their expertise to make the model run every day and be competitive. And so that's what's a colleague of mine has been developed this. So there's a whole family of HealthKit tools, ECMWF, and then the HealthKit Hydro is the one that supports hydrology. That, for example, is used Rust as an acceleration. So it really makes possible to have this the pre-processing of data, made it in a very efficient way. And then there is another colleague has been working on developing a kind of a dashboard. And the reason for that is that this allows other people in the team to then really look at the model and play and analyzing and yeah, in case in real time. So the future work is so kind of what's I think what the idea of ECMWF is, at least of my team, is to try to get something out, get the whole pipeline working. So as you saw, the results are okay, are competitive with Google, but it's not the best model in the world. But then we have all this pipeline working. So the model is already running now twice a day. We already have a dashboard. And so everything is kind of like we've closed the circle. And now we can go with the second circle, which is to add more. So try to improve the forcing data, try to improve the static data, try to play with different architectures. As I mentioned before, the state space model seems to be an interesting avenue. And then again, look at the loss function and pre-training on this synthetic data and so on. And another avenue is the probabilistic model, which is also kind of a parallel effort. Whereas what I'm actually currently working on is developing a model which is of higher resolution. So the model I've shown before is a daily model, whereas I'm now focusing on a 6-hourly model only for Europe. And the challenge in Europe is that we have a lot of human intervention. So whereas Caravan and the kind of the data we used before were like a natural river, in Europe, you really do not have many natural rivers. So that's a main challenge of these European models. So the high resolution and the fact that you have quite a lot of human intervention. And then in operation, something that's my colleagues are starting doing is to really try to compare it with other operational model. So we're now retrieving in-house the Google forecast as well. And then we all do event-based analysis. So that's kind of can then drive research. So if we see that the model is really not performing well in some situation where we want it to perform better, then we can kind of learn it by the verification. And finally, some events is that we will be at EGU. So yeah, come to say hi. Really be happy to to chat and get your ideas. And then I think one nice, if you're interested on ECMWF work, a nice way to engage is Code for Earth initiative. So have a look. Quite some people that work at ECMWF have been kind of joined one of the challenges in previous years. And that's also a bit of a nice way to get to know how the organization works and the type of work we do. So I think they will be in the coming months. So they're not all the new challenges are not open yet, but in the coming months they will be open. So yeah, just keep an eye on the space. So key takeaways is that flat forecasting is challenging, but it's extremely important. So we are developing. We have developed the first version of this AIFL, and which is now kind of we've closed. As I said, we've closed the loop. Simple model. A lot of things can be improved, but at least we got somewhere, and the model is comparable to Google. And I failed to say that actually it seems to really outperform the physical model. But again, it's probably too soon to say, and we want to do some more verification in-house. And that's the operation are efficient. So the model runs very quickly in I think it's 20 seconds for the global model. So it's that's very, 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 very important. And the communication that's also that's also important. So especially in within our team to make sure that the model gets verified. And yeah, so that was all for me. Yes, I see a question. I don't know, Miranda. So, oh no, maybe there was not.
I think it was just emoji clapping.
Okay, thank you.
Although if anyone does have any questions, either locally or online. Naomi, you have a question? Do you want to pass it towards my laptop?
What would you say was the biggest challenge in converting from like academic code to operational code?
Well, I think so. Let me think. So I think if you have a really good research code, I think you're ready to go. I think I kind of think that for me the most challenging. So it's kind of like at least on the web, there is that way to try to make things operationally immediately. It's kind of that push to always have things kind of made operational. So that I think that's for me challenging. But I would say it's actually not really different than academic research, because then you have actually teams that really help you and support you. So as a researcher, I don't think it's really different than doing research at university. Of course, if your code is applied, because then you're just gonna hand over the code to a team or to other people that have know how to optimize it, and it's kind of being taken care of. But of course, there is always that kind of push to make things. To make things working, which kind of a bit is in opposition to a research focused work where you want to actually have like the best model, but the kind of the approach is a bit on getting things out and tested. And I mean, out, for example, now the model is only like we cannot say it's not public yet. So once we're gonna be sure of the model, then we're gonna make it public, because of course you have reputation that you want to maintain. But in order to kind of have it, so to really work as a team, then you also need to share it, and that's kind of making operational and making this web page is a way to share it with the rest of the team.
We said thank you in case you didn't catch that. I think Jesper, who is online, has a question. Do you want to type it or unmute yourself?
Oh, that's fine. Hi. Yeah, first of all, looks like a lot of work, so pretty impressed from this side. I stuck to something that you mentioned it in the beginning and in the end of your talk, and that was kind of the intervention of humans to all of those river networks. And I guess if dams are being built, or even the natural morphology of the rivers changes within like a time frame of 20 or 30 years or more, and I guess that this changes quite a lot the relation between precipitation and runoff and the hydrographs. And you mentioned that this is a problem, and I was just wondering, is there any techniques or things to kind of handle that? Or is the model smart enough to know that, e.g., if there's a dam being built, that it knows, okay, after a certain date, I will have to handle the relations differently and things like that?
Yeah. So up to now, so I'm only developing now this European model where we expect the dams to be of a major effect. So I don't really have an analysis yet. The problem with dams is that the release is often not public available. So the operators don't really give the data. So we do have data in, so I'm reusing kind of the data that they use in GloFAS in this physical model. So where there is a whole team that is trying to to kind of calibrate and then fit and try to get some this release, and then they have different they call it degree of regulation, and so kind of try to see what the impact of this dumps is on the downstream gauges. So up to now I'm only using those, kind of restricting myself to those data. What I think it will be really interesting is to have a part of the network that is learning that, kind of to learn how the human decides to kind of to operate, because sometimes it's really like a human decision. So that will be my kind of my interest. Will be I think it will be an interesting research topic to look at. But up to now, we'll just run the model with this kind of GloFAS with this data that are already used for the physical model. And then once I will see that the model is really struggling because of what we expect to be human intervention, then I could start thinking of this part of the network that is learning that.
Okay, thanks.
There's another question in the chat, Maria Luisa, from Mendrika, who says, thank you for the presentation. Did you use a specific technique for AIFL to embed the inputs before the LSTM parts, or did you just use standard neural network?
Yeah, just standard. Not sure if she has or they have any other suggestion, maybe if they're looking into the space. But yeah, just standard embedding, feed-forward neural network, and then the inputs are fed into the LSTM.
I have a question about the ensemble methods. I think I got a little bit lost when you're talking through. I was curious how you combine those. Is it like because you got the ensembled numerical methods before they get fed into the network? I was wondering if you could go into a bit more detail.
Yeah, so up to now we have not. Up to now it's only a deterministic model. So we run the deterministic model 50 times for the 50 ensemble members. And the reason for that is that we haven't really created a data set yet with all the past ensemble members for this. So we only had, so we really haven't, we've just developed, we've just developed a deterministic model, and then we run it 50 times. That's when I said that a probabilistic model is kind of like one of the future work that's really to try to learn the distribution. So to have, not step away from this deterministic approach.
Thank you. I guess a follow-up would be, how are those ensembles collated into the neural network? Do you just feed them all in raw? Are they weighting between them, or just the statistics, or?
Yeah, no, it's just we don't weight them. Because I think that already the 50 ensemble members are chosen to be. So there is a choice where there are 50. So I'm not sure if we should be weighting them. But this is really outside my comfort zone, so I'm not sure. And the way they are, like the way the results are presented, again, I've not looked into that, because they are just because the GloFAS model works the same way. It's just run 50 times, and then it produces it produces 50 different deterministic forecast. And then they are so the way they are presented is kind of the same way they are presented has been applied to our model. But I'm not really sure how that is how we're doing that now.
Thank you very much. Do we have any more questions?
Yeah, we have one more question. It's Jesper again, but it's actually inside DHI here from Kassel. So I'll just relay the question to another of my colleagues over here.
Yes, hello. Hi, Maria. Thank you very much for this, and congratulations to this impressive work. You mentioned, I have two things that I would appreciate if you could say a little bit more about this. And the one was that the choice of the LSTM at the beginning. You mentioned you also considered graph neural networks because of the network of hydrological systems and the upstream downstream dynamics, and it seems to be I mean, just looking at it, it seems to be another interesting choice. But you said that there's not so much literature. But like, have you done other comparisons, or is there any ideas for the future to maybe try that instead of the LSTM?
Yeah. So yeah, that's somewhere we want to go to. So we're closely looking at Google, what Google is doing, and they developed a graph, a global graph neural network. However, what they say is that it's much heavier to run in operation. Of course, the LSTM is very light, but it's much heavier to run, and it actually does not really outperform the LSTM. But what they use it is for data simulation. So once they have real data, once they have real observation, then they update the state of the network, and they can kind of propagate that update through their graph. So that's kind of where they see the advantage of the graph neural network. But again, when they keep presenting the work, they keep presenting for 3 or 4 years. They've been presenting always the same slides. Hence, we're a bit, we're not really sure. And from other literature, we haven't really seen any global graph neural network. It's also kind of, I mean, in Europe, we have a very well-defined connectivity between the stations, but in the rest of the world, we have very sparse observations. So we're also not really sure how to use that. Whereas a model that is very interesting is River Mamba, which has been published in NeurIPS, the last NeurIPS. So we're actually also talking with Hakam, who's the developer, and he uses a Mamba model, state space model. And then he kind of his model is also fully distributed, and that seems to be quite competitive. So that's a bit the space we're a bit looking at to try to see if his model could be a replacement for the LSTM. So definitely the way we want to approach it is to have a fully distributed model, because that will make comparison with our physical model also possible, because as now we just have some few points in the world, but it's not really comparable with a fully distributed model. And also hydrologists in our team really want a fully distributed model. But as now we haven't seen clear evidence in the literature that we should step into because of course graph neural, like a global graph neural network would be a much heavier model to train and to run. So that's why we're watching the space, but we're still kind of stay with the state of the art, which seems to be the LSTM. But yeah, not sure what your view is, or have any recommendation.
I mean, this was thank you. This was already like the type of answer I was looking for. So we are also, I think we are. Yeah, I mean, exactly. It reflects, I think our knowledge also reflects what you're saying, that the graph neural network seems very interesting, but there's not so much in the literature that we see that actually has done it or is outperforming the LSTM so far. Yeah. Thank you.
Thanks.